Welcome back. We're still talking about performance issues for an inverter, for example. And what we're going to be looking at is basically the fall time and the rise time. This is how we picture the fall time. We have a load capacitor. Initially it's going to be discharged through the NMOS transistor, which looks like a current source, so that's going to be relatively easy to calculate. And then we're going to transition into the regime where the NMOS device looks like it's in a linear regime, and it'll look more like a resistor. And again, relatively easy to calculate. So when we're in saturation, the output voltage is greater than VGS minus VTN. When in the linear region, the output voltage is less than VGS minus VTN. It's a straightforward method of estimating the fall time, and that is accomplished by dividing the operation of the NMOS transistor into those two regions that we just talked about. That's the linear and the saturation region. So the fall time is going to consist of two components, TF1 and TF2, and they're defined as follows. TF1 is the time for the output capacitor to fall from 0.9 VDD to VDD minus VTN. TF2 is going to be the time for the output capacitor to fall from VDD minus VTN to 0.1 VDD. And to keep in mind that the current out of the load capacitor equals the current to the NMOS transistor. Effectively, they're equal and opposite in KCL. So the current, in this case into the load capacitor, is equal to the current out of the NMOS transistor. In this case we'd have CdVdt equal to the current flowing out of the NMOS transistor. That's why we have a negative sign there. So the left hand side is current flowing into the load capacitor, the right hand side is the NMOS transistor in saturation, and it looks like a voltage independent current source. There's no V out on the right hand side of the equation. And the voltage region of interest is 0.9 VDD through to VDD minus VTN, at which time it would then transition into the linear regime. TF2 is the very same principle. We equate the current flowing into the load capacitor, CdVdt, or the current flowing into the load capacitor, as being equal and opposite to the current in the NMOS transistor when it's in the linear regime. So as a consequence now we see that we have a function of V out. So the left-hand side is current flowing into CL, right-hand side NMOS in the linear regime. It looks more or less like a resistor, and the region of interest again is going to be VDD minus VTN as the output voltage drops to, let's say, something like 0.1 VDD. These equations can now be integrated, and we'd solve for the overall fall time as it being equal to TF1 plus TF2. And the solution for TF1 is trivial. We're going to integrate the current flowing into the load capacitor from VDD to VDD minus VTN as being equal to the current flowing, I guess in this case, out of the NMOS transistor from time 0 to TF1, and we're just going to solve for TF1. And that's relatively straightforward to solve for. TF2 is a little bit more difficult. We'd end up with the same type of equation up here, the same type of integration, but the limits would be slightly different. And we'd end up with something like this. This is what someone else had generated, but it leaves a nice in-class assignment. It doesn't look right, so you're asked to please fix it. If you can't fix it, then let me know how you know it's incorrect. And the hint for that should be along the lines of dimensional analysis, and you just make sure that dimensions are consistent on the left-hand side and the right-hand side. So you can probably get close to an estimate with relatively crude estimations. For TF1 you don't have to use any estimation whatsoever. It's relatively simple to integrate that equation. Everyone here I'm sure can do that. TF2 is a little bit more difficult, but what I'm going to do here is I just wrote out the equation and simplified my life a little bit by throwing away the quadratic term, which made it a little bit easier to integrate. And I'm left with something that at least is dimensionally correct, and probably close to something on the order of what TF2 would be, even if I took into account that quadratic term. In any event, if I start plugging in some values then when I add TF1 and TF2 together and let the threshold voltage be 0.2 VDD, I come up with a pretty useful approximation for the fall time, which is 4CL over beta VDD. So that's a good one to remember. A good back of the envelope type of calculation for estimating fall time. Is it a reasonable approximation? Well, you can check it against a simulator of your choice, and I'm sure you'd find it's not too bad. It does provide some insight into the discharge process. It's an RC type of discharge, as you'd expect. The numerator you can think of as being 4CL is a conservative estimate for the load capacitance. And the denominator, beta n times VDD all to the minus 1, is a reasonable approximation for the resistance of the NMOS transistor in the linear regime. And that came from the current equation you had for the NMOS transistor previously. This allows you to look at some considerations for design trade-offs. Some are obvious, some a little less so. If you go back to the approximation for the fall time, you'll see that you could decrease the fall time by increasing beta n, and you could also decrease the fall time by increasing VDD. So locally you might be able to get away with increasing VDD to increase the speed, but increasing VDD comes with some consequences. It's increased power dissipation, increased hot carrier injection due to increased electric fields, which means you may not be able to fabricate the transistor. I think the hot carrier injection here basically means that you have a difficulty telling the difference between the device being on and the device being off. So really, to increase the speed, the voltage is decreased, as we saw with the scaling rules. Perhaps it's not so obvious, but you can take a guess, and it's probably going to be related to being able to manufacture the device and make it smaller. And if you make it smaller, it's going to be faster. At this point in time, we'll take a brief break.